So we're going to start talking about trigonometric functions today. And before we start talking about trigonometric functions, I want to introduce something which is called the unit circle. Now, the unit circle is something that we're going to be making use of quite a bit here. So you want to get used to what this is and how it works. And really, the unit circle isn't anything too complicated. If I think about the XY plane, and I think about, let's put some marks here at x equals 1, y equals 1, x equals minus 1, y equals minus 1. I can think about the set of all the points which are a radius of 1 away from the origin. And if you think about what would that equation look like? Well, all the points that are a radius of 1 from the origin, those are going to be the points whose coordinates satisfy x squared plus y squared is equal to 1 squared. This is a consequence of the Pythagorean theorem, because to say that something is a distance of 1 from the origin, well, if I think about a little triangle here, whose base is the x-axis, and whose height is given by this perpendicular dotted line here. Well, it's not really dotted anymore now that I moved my marker over it, but it was dotted a moment ago. If I think about this, well, this point here is going to be some point x comma y, and the base of this triangle is x, the height of this triangle is y. The Pythagorean theorem tells me that the square of the bottom plus the square of the side equals the square of the hypotenuse. And if you look at what do all of these points look like, well, the answer is, let me just erase this here really quick so that the picture doesn't get super messy. You get a circle, because it's really just all of the points that are a distance of 1 from the origin. Now, I cannot draw a circle, so you're going to have to pretend that this is a circle, because I just am incapable of drawing them. Now, this is called the unit circle to differentiate it from other circles that might have a different radius. We call it unit because the radius is 1. It turns out that the unit circle is going to be the way that we want to define these functions called trigonometric functions. But before we get to that, we need to say a few things about angles and the unit circle. So let me leave this picture of the unit circle up here, and let's talk about the standard definition of angles on the unit circle. So how do we think about these angles? Well, the answer is that an angle of 0 is going to be an angle that points to the right and just goes along the x-axis. So 0 points along the x-axis. This is sort of our starting point on the circle. And remember, we talked about what is an angle, and we talked about radians in a previous video. So if you don't really remember what we said about radians and measuring angles using radians, then you might want to go back and double check on that. Just review it really quick and see what we said about that. Now, the way that we're going to use these angles on the unit circle is a positive angle. That's not how you spell positive. Positive angles go counterclockwise, and negative angles go clockwise. Why do we have this convention? Well, we could have chosen to do it the other way, but the main reason that we have this convention has to do with some things in mathematics that when you do things this way, they work out right-handed. If I were to put my right hand on the board like this, then the positive direction for an angle is the direction in which my fingers sort of naturally curl. And that's really kind of why I think they have this convention. We could have, of course, chosen to say positive angles go clockwise, but the convention is that positive angles go counterclockwise. Now, If I have some angle on here, let's call that angle theta. Well, remember that the radians just tell me the distance around the edge of this circle that I go as I'm moving along here. In fact, it's really just the distance in this case because this circle has a radius of 1. So normally the angle tells me how many multiples of the radius I've moved around the edge of the circle, but in this case, it really is just telling me the distance because the radius is 1. So if I multiply radius of 1 times the angle in radians, that just gives me the distance, which turns out to be equal to the angle in this case. And that's really one of the reasons why we like working with the unit circle. The fact that the radius is 1, that really makes things much more convenient for a lot of purposes. So let's just take a look at a few examples of angles on here. Again, I'm going to try to leave this up and just sort of adjust things on it. But I do want to erase a few things just to make sure we don't have a complete mess here. So an angle of 0 would be the angle straight along the x-axis. If I wanted to go around 1/4 of the circle, remember how much 1/4 of a circle is in terms of radians? It's pi over 2. So the angle that is actually a right angle up here, this is an angle of pi over 2 radians. If you wanted to think about it in degrees, you could also say it is 90 degrees. Sometimes we will be working with degrees. Most of the time we want to stick with radians, but you want to know how to do it in degrees as well. If you wanted to go all the way over to this side, so in other words, pointing negatively along the x-axis, well, that would be going around half a circle. And half a circle, we said, is pi in radians. You can also think of this as 180 degrees. If we went around 3/4 of a circle, so that would be go all the way around the circle like this, come down to this point down here, well, that is going to be pi radians plus an additional pi over 2 radians that I've gone. So that's going to be 3 pi over 2 radians. You can also think of that as 270 degrees. And if we were to go one complete circle, we would end up back where we started at 2 pi radians, which of course is the same thing as 360 degrees. This is not surprising. We defined radians in a way that 2 pi of them is a full circle, and we defined degrees so that 360 of them gives me a full circle. So this shouldn't really come as a big surprise, but it's good to double check, make sure that everything is working out nicely like this. Something that I want to notice here is that we got back to where we started. And that means that in some sense, as you keep on going around with different angles, you keep on going through the same points on here. And in order to talk precisely about what we mean, we need to define something called the terminal point. The terminal point of an angle theta is the xy coordinates where the angle hits the unit circle. Sorry, this board is a bit small, so I'm having a little trouble fitting everything in here, but hopefully that's a little bit legible. So, in other words, the terminal point, if I have some angle theta, so here's my angle theta, the terminal point would be right here, this thing that I've placed the arrow pointing towards. So let's think for a moment about these angles here that we were talking about, and let's think about what are their terminal points. If I were to go around by pi over 2 radians, this terminal point is going to have the coordinates 0, 1. I can see that just by looking at, hey, here's a point on my Cartesian plane. I'm just asking, what are the xy coordinates of that point? If I were to go around to pi radians, this point over here is going to have the coordinates -1, 0, because we're at x equals -1, y equals 0. So you can probably kind of see the pattern here. What would the terminal point down here be? Take a moment to think about this, and then the answer is going to be, well, down here at this point, I'm going to be at x equals 0 and y equals -1. What about the terminal point for an angle of 0? Well, that's just going to have the terminal point 1, 0, because we're at x equals 1 and y equals 0. Now, the thing to notice is that points like 1, 0, this is the terminal point, which I'm just going to abbreviate as TP here, for 0, but also it's the terminal point for 2 pi. And this is something that we can actually kind of generalize from this. We can take this idea that, hey, look, if I do 2 pi, I go around the circle 1 complete time. Well, if I go around the circle 1 complete time, that doesn't change the terminal point. So one thing that we can say is that if, you know what, I'm going to erase this so I have a bit more room to write here. Hopefully you guys are taking notes and have already drawn your own unit circle that you can refer to for a few moments here. So if theta 1 and theta 2 are angles in radians, and if the difference between them, theta 2 minus theta 1, is a multiple of 2 pi, and that just means that theta 2 minus theta 1 is equal to 2 pi times k, where k here is some integer. Well, in that case, they have the same terminal point. And so for a lot of purposes, these angles are going to be kind of the same angle. They give us the same terminal point on the unit circle. Basically, two angles that differ by a full traversing of the circle, a full rotation of the circle. They're really kind of geometrically the same thing, even though we're kind of calling them by different names. But they're really, for many purposes, they're just the same. If you prefer doing this in degrees, in this case, the difference is a multiple, which apparently I can't write, of 360 degrees. Again, this is what you would expect, right? Because we're saying basically two angles have the same terminal point if they differ by one complete circle. Well, one complete circle, if I measure it in degrees, is 360 degrees. So one complete circle, we get the same terminal points. So this is how we can think about angles and the unit circle. And I'm going to break there for the moment, and then in the next video, I'm going to talk about how this allows us to define what are known as the trigonometric functions. So I will see you shortly.